Hello there, and welcome to this video on reciprocal functions. We're going to split our reciprocal functions up into two different parts. The first part is going to be on linear functions, so everything is going to be a line. And then in the second part, we're going to do on quadratics, and then that's when it'll have that kind of horseshoe shape. So a reciprocal function, the definition for that, it says a reciprocal function is a function written y equals 1 over f of x, and f of x cannot equal 0. So f of x is just really some other function that we've seen. Today we're going to be looking at linear, so it's going to have the form mx plus b. So m and b, these are just going to be some numbers. They could be positive, negative, decimals, they could be fractions, but it'll look something like that. So what we're going to do here first, we got a table and a graph. We are going to graph or sketch the function f of x equals x, and really that's just the function y equals x, and then after we're going to sketch the function y equals 1 over f of x, which that will be y equals 1 over, and then f of x was just x. So it's the reciprocal function. You basically took this and you took the reciprocal, so it just flipped down to the denominator. So let's first find some points for y equals x. So if y is equal to x, if x is -5, then y is also -5. If it's -2, then y is also -2. And you can see we're just going to keep getting these numbers all the way down. And then what we'll do is we'll plot some of these points. So -5 and -5, that would be right here. -5 and -5. -2 and -2, that would be right here. And then I'm just going to continue to plot on the rest of my points. And now that I have all those points, I'm going to take my ruler and draw a line through those points. And then don't forget your arrow at the end of your line. So that is for the function y equals x. Next, we're going to find some points for the function y equals 1 over x. So basically you take what you had, x, and then it just gets flipped down into the bottom of a fraction. So if we had 5, now it's going to be 1 over -5. And then -2, that's going to be 1 over -2. And you can see this trend is just going to continue all the way down. Now 1 over 0, you can't divide by 0, so for that we're going to get undefined. Then we're going to have 1 over 1. That one will just simplify to 1. This one up here could also simplify to just -1, and then 1 over 2, and then 1 over 5. So now I'm going to plot those points. So the first one at -5, we're at 1 over -5, so that's a very small number. That's -0.2. So we're going to be over at -5 and then down 0.2. So that is going to be right about there. And then the next one at -2, we're at -0.5, so -2. We're at -0.5. Then it was right here, -1 with -1, so that's this point. And then the next one, at 0, we were undefined. And then at 1, we were at 1. So that's going to be right there, overlapping on that other point. And then at 2, that's right here, we're at 0.5. So we are right there. And then at 5, we're at 1/5. So again, we're down really close to 0, 0.2. So you can see with these blue points, it was kind of going like this, and then it was going to curve up. We can't ever cross here at 0, because at 0, it was undefined. That means you can't have a point there. So what we actually get with our reciprocal functions is wherever this original function crossed, that is going to be an asymptote. It's basically a line that you can't cross. So I cannot cross right here. So this is just going to kind of curve down, and this one's going to come like this, and then it can't cross here. So it's just going to curve up. So I'm just going to draw that on there now. So we get that blue graph. And again, I said there's this asymptote that is right here. And you can also kind of see we can't cross here either. So there's actually an asymptote there. And we'll talk about those down below in a sec. So I'm just going to draw those two asymptotes on now. So that would now be our complete graph. So next we're actually going to look at our asymptotes. So it says an asymptote is a line whose distance from a given curve approaches 0. So we can see with this blue line, it gets really, really close to this pinkish line here, but it never actually crosses it. So it approaches a distance of 0. It gets very, very close. A vertical asymptote for reciprocal functions occurs at the non-permissible values of the function. So that was like right here. We couldn't take 0 and go 1 divided by 0. You can never divide by 0, so that we got a asymptote. So if I were to label it, it would have been x equals 0. That's where that asymptote there was, the vertical asymptote. The next point describes a horizontal asymptote. So a horizontal asymptote describes the behavior of a graph for a very large positive and negative value of x. The line y equals b is the horizontal asymptote. So that is going to be right here on this one. So that is the line y equals 0. And for all of our graphs, actually, the asymptote, the horizontal asymptote, is always going to be at y equals 0. And just to explain this part where it said very large positive and negative values of x, that is this right here. As this goes very, very large, it's going off and it's getting close. And then as it goes this way, we're getting a very large negative value, and it's getting very, very close to that one as well. So I'm just going to write down here at the bottom our horizontal asymptote. It's always going to be y equals 0. And if I asked you the question why, if you wanted to think about that first, you can. But the reason why is because if you had some function like y equals, we'll pick an easy one, 1 over x, and then you tried to make that equal to 0, you can never find a value here that will get you out a 0. So this value right here, the y, that can never actually be a 0. So we have an asymptote at y equals 0. So that's kind of the reasoning why. But you guys can just remember it always happens at y equals 0. So next we have invariant points. And if you have an invariant point, the word vary means to change. So if it's invariant, that means it's not changing. So these points do not change. So it says a point that remains unchanged when a transformation is applied to it. So that's when we take the reciprocal function. That's what the transformation would be. So these are always going to occur at y equals positive and negative 1. So we just change the y to be a positive and negative 1, and then that is what we solve. And the reason why our invariant points happen at positive and negative 1 is because if you took 1 and then you take the reciprocal of it, so that'd be 1 over 1, you get the same thing, so it didn't change. Or if you had negative 1 and then you take the reciprocal of it, that's 1 over now negative 1, you still get negative 1, so it didn't change. So that's why those are our invariant points, because they don't change. Any other number, when you take the reciprocal, it's going to change. So next now we're going to get into our first example. It says, for the following functions, sketch the function and the reciprocal. Identify the zeros, asymptotes, invariant points, domain, and range. And for the first one, this is our function. F of x equals 3x minus 9. So let's first begin by finding the zeros. So the zeros, this is where it's going to occur where y equals 0. So it's where it crosses the x-axis. So if you want to find the zeros, you just change y, which this is y, right? So we want to change that equal to 0, and then we can solve and find the zeros. So I'm going to do that just down below here. So our zeros, our function was f of x equals 3x minus 9, and then I'm going to change the y, f of x, to be 0, and then solve for x. So you can add a 9 onto both sides. We'll get 9 over here equals 3x. Divide both sides by a 3, and you'll get x equals 3. So that would be your 0. So let's just go back up. We'll write that back on. So our 0 is going to be when x equals 3. Next we have our asymptotes. And one asymptote always is going to be y equals 0. If you want to write in always there, it's always going to be at y equals 0. And then the other asymptote occurs where the 0 was. So we already found that. So our other asymptote is going to be at x equals 3. So maybe before we go any further, let's actually start to graph some of this. So if we graph the function y equals 3x minus 9, this is your y-intercept, so it's going to cross down way at negative 9, which is off our graph. But we also knew that it was going to have a 0 at 3. So at 3 over it's going to cross right there. That's our x-intercept, or our 0. And then the 3, that is your slope, and that is really 3 over 1. So you're going to rise 3 and then move over 1. So rise 3, 1, 2, 3, move over 1. We'd get that point right there, and you could continue it. We'd get another point right there, and then you could take your ruler and draw your line through those points. So that is the original function f of x. And then our asymptotes, let's also graph those on there. So that was these right here. So at y equals 0, that one's always going to occur at y equals 0. So that's going right through at the x-axis. So there's our 1, we can label it, y equals 0. And then our other one occurs where the 0 was, which was right here. So it's going to go through that. And this is our vertical asymptote. So we can just sketch it through that. And then don't forget your arrows. And then labeling this one is x equals 3. Now if we wanted to sketch the reciprocal function next, we knew that it was going to have 2 points on it that did not move when you flip them. And those were at 1 and -1. So at a height of 1, that's right there. And then at a height of -1, that's right there. So both of those points do not move. So you can plot those points, and then to sketch your graph of it, you're going to have to go through that point, but you can't cross these pink lines. So this one's going to have to start here, come down, go through it, and then can't cross this line, so it's got to curve and then go that way. And then this one's got to come, go through the point, can't cross the pink line, so it's got to curve and then go up. So I'm just going to draw those on there like that. So those blue lines right there, that is our reciprocal function. So next we're actually going to find these invariant points, and those were right here and right here. So those occurred where y was equal to a positive and a -1. So I'm actually going to solve for those just down here. So at our invariant points, we're going to have y is equal to +1 and y is equal to -1. So our original function was this, y equals 3x minus 9. And then I'm going to change y to be a +1 and a -1. So first let's do +1. So we got y changing to the 1, and then we'll solve this. So add a 9 onto both sides, so we get 10 equals 3x, and then divide both sides by 3, so we get x equals 10 over 3. So that's where we took the +1. Then I'll do one where we have -1, and we'll solve that one as well. So add a 9 to both sides. So we get 8 equals 3x, and then divide both sides by 3, so we get x is equal to 8 over 3. So this one right here, we got 10 over 3. That is where y was equal to a +1, so I'm just going to write that. X is 10 over 3, y is +1. And then the other one, we got 8 over 3, but that one was when y was equal to a -1. So those are going to be our 2 invariant points. So let's just write those back up at the top here. So it was 10 over 3 and -1, and then our other one was 8 over 3 and +1. The last thing that we have to do here is just find our domain for the original function f of x, that was the line, and then also the domain range for the reciprocal function, which was the blue right here. So looking at the red line, you can see it's just going to keep going up and up and up, and it's just going to keep going down and down and down. So it's getting all of the x's, and it's also getting all of the y's. So our domain for this is just going to be x, given that x is an element of the reals, gets every single number. And then the range, similar, y, given that y is an element of the reals, so you can get every single number. The domain and range, though, for the reciprocal function, this one's a little bit different. So we're only looking at the blue on here. Okay, so you can see for the domain, that's x values. It doesn't get this middle x value. It doesn't get when x was equal to 3, right? That's where we had an asymptote. We have this invisible dashed line there. It actually never crosses. So our domain is going to have to be x, given that x cannot equal 3, but x can be anything else. X is an element of the reals. And then looking at our range, that's up and down. So we can see the blue goes up, and then it starts a curve, and then it never gets to this point right here. It kind of goes like this, and then it skips to over here, and then it keeps going up again. So it never gets when y is at 0, right? Because there was an asymptote there as well. So really these asymptotes are what tell you your domain and your range. So our range for this is going to be y, given that y just can't equal 0, but y can be anything else. Y is an element of the reals. So that was our first example. Example number 2, if you feel confident enough, you could pause the video and then try to do the second one here by yourself. So I am first going to actually start with my sketch on this one. So I'm going to sketch y equals 2x plus 5. And this 5, that is our y-intercept. That's going back to your grade 10. So I'm going to plot my y-intercept there at 5. And then the 2, that's your slope. So our slope is really 2 over 1. So we're going to rise 2 and then run 1. So rise 2, 1, 2, run over 1. You always run to the right. So we'd get a point right there. If you wanted to go downwards, you could hop down, but then you just have to run to the left. So we'd hop that way, and then we get another point. You could do it again. 1, 2, 1 over, get another point. 1, 2, 1 over, get another point. And then you could erase those little hop markers if you'd like. So I'm just going to erase those just so I can see my graph a little bit better. If it was on a quiz, you could keep that on there just to show your work. But next, what we got to do is just take our ruler, draw a line through those points. So that is my original function, the y equals 2x plus 5. And remember, from the original function, wherever it crosses, so right here, that is what's going to give us our asymptote. So we're going to have an asymptote that actually cuts through right where it crosses. So that is one asymptote. We're going to find out exactly where it is later when we calculate it. And then our other asymptote is always at y equals 0. Okay, so that one, you should have no hesitation on a quiz. There's always an asymptote there at y equals 0. And then if I wanted to sketch my reciprocal function already, I know that it's going to have an invariant point at a height of 1, so right there, and then also at -1, so right there. And then again, just draw your lines going through those points, but they can't cross the pink lines, so they got to look something like that. So I'm just going to draw those on now. So those blue lines there, that is my reciprocal function. So now let's start to calculate all of these things over here. So let's start with our zeros. So remember our zeros, to calculate that was when y equals 0. So to calculate that, I'm just going to change my y here to be a 0. I'm going to do that down below. So it was y equals 2x plus a 5. And I'm going to change the y to be 0. So we just got 2x plus 5 still on the right. So subtract 5 from both sides, we'll get this. Then divide both sides by 2, and we get x equals -5 over 2, which as a decimal, that would be -2.5. So that's why it crossed here over. It was over 1, 2, and a half, so -2.5. So I'm just going to label this asymptote here now. It's x equals -5 over 2, or you could even say -2.5. Usually we like to use the fractions. So we can write in our 0 that we just found. It was x equals -5 over 2, which also gave us our asymptote, x equals -5 over 2. And then our y asymptote, our horizontal asymptote, is always y equals 0. And remember, that's always at that point. Next, we can find our invariant points. That's when y was equal to a +1 and a -1. So we're going to take our function and set it equal to a +1 and a -1. Again, I'm just going to do that down below here. So our function is y equals 2x plus 5. Then I'll change it into a +1 here first and solve that. So subtract 5 from both sides. Get -4 equals 2x. And then divide both sides by 2. So we get x equals -2. So that was for the +1. I'll do right over here on the left when we do the -1. 2x plus 5. So again, subtract 5 from both sides. Get -6. And then divide both sides by 2. So we get x equals -3. So these points, this left one, when x is -3, the y was -1, right? -1. And then our right one, when x is -2, our y was, we changed it to a +1. So those are our two invariant points. So I'm just going to scroll up and then write those down. So it's -2 and 1, and then our other one was -3 and -1. Okay, and then lastly, we got to do our domain and our range for both of our functions. Our domain and our range for a linear function is always going to be x can be anything and y can be anything. So those will never change for linear. And then our domain and our range for the reciprocal function, this one down here, our domain can be anything, right? We had all of the x's except we couldn't get to this x value. That was -5/2. So again, the asymptotes tell me what my domain and range are going to be. So x can be anything but can't be -5/2. X cannot equal -5/2. And then my range started here, went up, started to turn, and then it didn't cross this point, didn't cross at y = 0, kind of hopped to here and then kept going up. So again, this is going to tell me my range. We can have everything except y cannot equal 0. So that was our last example. If you tried that one on your own, hopefully you got most of that. Our textbook questions are just now here at the bottom. So it's on page 403, and for 1 to 5, you're doing just parts A and B.